Right now, as you sit here, the very space around you is stretching. It doesn't matter if you're in your bedroom, on a crowded bus, or walking down the street. Every single point in the universe is quietly pulling away from every other point. Galaxies drift farther apart, clusters spread across ever-growing voids, and the cosmos itself inflates at a rate so staggering it almost sounds like science fiction. But here's the part that really shatters our brains. This expansion isn't pushing into anything. There's no hidden room outside, no cosmic warehouse waiting to be filled, no bigger box that the universe is growing inside of. Space itself is the thing being created. It's like reality is pulling more of itself out of nothing with every passing second. And once you try to picture it, the paradox hits you like a brick wall. If the universe is getting larger, what is it getting larger into? How can something expand without an outside? Your intuition screams at you that there must be a boundary, some invisible edge beyond which lies something. After all, that's how everything in your life works. A balloon swells into the surrounding air. A city sprawls into nearby countryside. A fire spreads across the fuel it consumes. Every example you've ever known involves expansion into something else. So naturally, when scientists tell you the universe is expanding, your mind imagines a massive balloon floating in some kind of higher dimensional living room, growing larger as it pushes into emptiness. It feels logical, it feels obvious. But that picture is a lie. For more than a century, astronomers have wrestled with this idea because the truth is far stranger than the metaphor. Space isn't expanding into emptiness, it's manufacturing the very arena where expansion can happen. Think of it like drawing a circle on a sheet of paper. If you want a bigger circle, you need more paper. But the universe cheats. Instead of finding a bigger sheet, the paper itself grows larger, stretching out so your circle can keep expanding. The boundary between inside and outside doesn't even exist, because the act of expansion creates the very fabric you're asking about. That's why cosmologists say the question, "What is the universe expanding into?" is like asking, "What's north of the North Pole?" It's a question built on an assumption that simply doesn't apply. But that's just the beginning of the weirdness. When scientists first discovered the expansion of the universe, they thought maybe we were sitting at the center of some giant explosion, a cosmic blast, flinging galaxies away into some empty abyss. But the more they studied it, the stranger it became. The galaxies weren't moving through space. Space itself was stretching, carrying those galaxies along for the ride like raisins in a loaf of bread as it rises in the oven. From inside the loaf, there's no edge to push into, only more dough forming as the bread grows. And here's where the mystery deepens. This isn't just happening out there in the vast blackness of intergalactic space. It's happening everywhere, including right here in the space between your eyes and the screen you're looking at now. The only reason you don't notice is because the forces binding matter together, atoms, molecules, electromagnetic interactions, are unimaginably stronger than the gentle tug of expansion. But given enough distance, enough emptiness, the expansion wins, and galaxies drift apart in a way you can never reverse. So we're left with a universe that expands without an outside, grows without borders, and stretches reality itself in ways that defy every instinct you've ever had about how the world should work. And the strangest part, this expansion doesn't just explain where the universe has been, it dictates where it's going. Every future, every possible fate of the cosmos, from a slow fade into eternal darkness to a violent ripping apart of reality itself, comes down to the same impossible truth. Space creates itself from nothing. And if you think you understand what that means, just wait. The deeper we go, the more bizarre it becomes. When you first hear that the universe is expanding, your mind grabs the nearest metaphor it can find. For most people, that metaphor is a balloon. You picture the rubber stretching as air fills it, the surface getting larger and larger while everything printed on it drifts apart. It feels neat, simple, and easy to understand. The balloon grows. So of course it must be pushing into something, the air around it, the space in the room. Expansion in your daily life always works this way. Plants grow into air and soil, rivers flood into nearby fields, cities sprawl into the countryside. Nothing just grows by itself. There's always a container, a backdrop, a stage that makes the expansion possible. And yet, when we try to paste this familiar logic onto the universe, it immediately falls apart. Because here's the unsettling truth. The universe is nothing like your balloon. When space expands, it isn't pushing into some kind of invisible atmosphere. There is no cosmic living room surrounding it. There is no wall of empty nothingness waiting to be filled. The expansion itself creates the space you're imagining. Think about that for a second. The moment you ask, what is it expanding into? You've already made the wrong assumption. Expansion doesn't require an outside. Expansion is what creates the very concept of inside and outside in the first place. Try flipping the balloon metaphor around. Instead of imagining the balloon sitting inside your living room, imagine that the surface of the balloon is all there is. The two-dimensional skin of the balloon becomes the entire universe. There's no inside the balloon, no outside the balloon, just the surface itself, stretching. If you lived on that surface, you'd see everything getting farther away from you, but you'd never find an edge, walk in one direction forever, and you'd just loop around endlessly without ever crossing into some external realm. The expansion doesn't need a place to go. It simply makes more surface as it stretches. That's a closer picture of how our universe behaves, but even that still cheats a little, because we live in 3 dimensions, not 2. And when you scale the concept up to 3 dimensions, it stops being something your imagination can hold on to easily. This is where cosmology feels like it's deliberately messing with your head. Our brains evolved to make sense of trees and rivers and hunting grounds, not the fabric of space-time itself. We're wired to assume that everything grows into something. So when scientists say space is stretching, we want to picture it like a balloon, or like dough rising in a pan, or like ink spreading across paper. But none of those images quite work, because they all sneak in an invisible backdrop. They all imply a surrounding environment. The universe has no such backdrop. The backdrop is the thing being created. That's the leap that breaks your intuition and forces you into the bizarre world of relativity, where common sense fails and mathematics becomes the only reliable guide. To show how deep this illusion runs, consider how even brilliant scientists struggled with it. Albert Einstein himself originally rejected the idea of a dynamic universe. His equations suggested space should be stretching or collapsing, but the picture felt so absurd that he assumed the math must be wrong. He patched his formulas with what he later called his greatest blunder, a fix designed to keep the universe static, because he simply couldn't accept the idea of expansion without an outside. It took observational evidence decades later to prove that his original math was right all along, and his attempt to protect common sense was the mistake. That's how deeply the balloon illusion grips us. Even Einstein tripped over it. And once you see past that illusion, the universe becomes far stranger than the balloon ever suggested. Because if space isn't expanding into anything, if it's simply generating more of itself everywhere, then the real mystery isn't where expansion goes, it's what expansion means. Why should the fabric of reality grow at all? What force keeps creating new room for galaxies, stars and planets to spread apart? The answers lead into redshifts, cosmic horizons, and the invisible hand of dark energy, each one stranger than the last. And this is only the first crack in the wall of our intuition. The deeper you go, the less the universe behaves like anything you've ever known. In the early 20th century, the universe most people imagined was static, eternal, and unchanging. The stars twinkled in fixed constellations, the galaxies seemed like distant decorations, and time itself appeared infinite. Even Albert Einstein, working with the revolutionary equations of general relativity, assumed that the cosmos must be steady and unmoving. His math told him otherwise. The equations demanded expansion or collapse. But the very idea sounded so absurd that he introduced a correction term to force the universe to stay still. He couldn't accept what his own logic was whispering. Then, a few years later, a man with a telescope would reveal the truth that shattered everything. His name was Edwin Hubble. Working at Mount Wilson Observatory in California, Hubble began meticulously cataloging spiral nebulae, those cloudy smudges in the night sky that astronomers couldn't agree on. Were they nearby gas clouds inside the Milky Way? Or were they whole galaxies unto themselves, so distant that their light needed millions of years to arrive? To settle the debate, Hubble turned to a particular kind of star called a Cepheid variable. These stars pulse in brightness at rates directly tied to their intrinsic luminosity, which means that by measuring the timing of their pulsations, you can figure out exactly how bright they truly are. Compare that true brightness to how bright they appear from Earth, and you get distance. It's like having a cosmic yardstick built into the stars themselves. When Hubble applied this method, the results were staggering. The spiral nebulae weren't nearby clouds. They weren't even part of the Milky Way. They were entire galaxies, each one filled with billions of stars, and they were unimaginably far away. Overnight, the universe exploded in scale. The Milky Way was no longer the whole cosmos. It was just one island in an ocean of galaxies. But this was only the beginning of the shock. As Hubble plotted the distances of these galaxies against the wavelength of their light, a strange pattern emerged. The light from almost every galaxy was stretched toward the red end of the spectrum, a phenomenon known as redshift. In everyday life, you experience something similar as the Doppler effect. When an ambulance rushes past you, its siren sounds higher-pitched as it approaches and lower-pitched as it recedes. With light, the same thing happens. Objects moving away from you have their light stretched into longer, redder wavelength. At first glance, this seemed to suggest the galaxies were racing away from us through space, as though Earth sat at the center of a grand cosmic explosion. But Hubble noticed something even stranger. The farther away a galaxy was, the faster it seemed to be receding. Double the distance, double the speed. Triple the distance, triple the speed. The relationship was perfect, mathematical, undeniable. This was no ordinary explosion. Explosions fling matter into surrounding emptiness, with debris flying outward from a central point. But in Hubble's data, there was no center, no preferred location. Every galaxy was retreating from every other galaxy in proportion to distance. This could only mean one thing. Space itself was stretching. The galaxies weren't racing through some pre-existing void. They were being carried apart, because the very fabric of the universe was expanding beneath them. It was as if the stage itself was growing, dragging the actors along with it, whether they wanted to move or not. This revelation demolished the idea of a static universe. It proved Einstein's reluctant equations correct, and forced humanity to confront a reality so bizarre that it still feels unnatural even today. We weren't sitting in the middle of an explosion. We were embedded in a fabric that creates more of itself every second. The redshift of starlight was the signature of this process, a cosmic fingerprint showing that photons traveling across billions of light years were being stretched by the growth of space itself. The longer the journey, the greater the stretching. That's why light from the farthest galaxies arrives at our telescopes, diluted into faint red embers, their once blazing ultraviolet fire transformed by the relentless expansion of the universe. Think about what that means. When you gaze at a distant galaxy, you aren't just looking across space, you're looking back in time, watching light that has been bent and stretched on a billion-year journey. The deeper you look, the younger the universe appears, and the more extreme the stretching becomes. Hubble's law isn't just about galaxies fleeing from each other, it's about the very nature of time and distance. The realization that the farther away something is, the stranger its reality becomes. And the most haunting part is that this stretching never stops. The universe doesn't coast along politely, it continues to expand, pulling galaxies apart faster and faster, until the question isn't just how far we can see, but whether there are regions of reality we will never see at all. Every night when you step outside and look up, it feels like you're staring into infinity. The stars scatter across the black canvas, galaxies appear as faint smudges in telescopes, and the sheer scale tricks you into believing you can see forever. But this feeling is an illusion. You are trapped inside a cosmic prison, and the walls aren't made of metal or stone. They are made of time itself. The universe may be vast, perhaps even infinite, but you can only see a fraction of it, a fragile bubble of visibility called the observable universe. Here's how the trap works. Light has a finite speed. It races across the void at 86,000 miles per second, fast enough to circle Earth 7 times in 1 second, but still not instant. When you look at the Sun, you see it as it was 8 minutes ago. When you look at Alpha Centauri, the nearest star system, you're seeing light that left it over 4 years ago. When you peer at the Andromeda Galaxy, that fuzzy patch in the night sky, you're seeing 2.5 million years into the past. The farther out you look, the deeper into history your eyes travel. But history has a beginning. The universe itself has an age of about 13.8 billion years. That means the oldest light that can possibly reach us has been traveling for 13.8 billion years, no more, no less. Anything farther away might exist, but its light simply hasn't had enough time to arrive. From our perspective, it may as well be invisible. Now here's where it gets strange. You might think this means the edge of the observable universe should be about 13.8 billion light-years away. Logical, right? But cosmic expansion complicates everything. While light has been racing toward us for billions of years, the fabric of space itself has been stretching beneath it. That distant galaxy, whose light began its journey when the cosmos was just a baby, has been carried farther and farther away in the meantime. By the time its ancient light finally reaches our telescopes today, that galaxy is no longer 13.8 billion light-years away, it's more like 46 billion. Expansion has moved it far beyond where it started. This creates a bizarre situation. We see the light from a galaxy that no longer occupies the position where that light was emitted. We are looking at its ghost, its past self, while its present self has slipped out of reach. This is the invisible wall of the observable universe. It surrounds us in every direction, a sphere with a radius of roughly 46 billion light-years. Beyond it lies more cosmos, perhaps infinitely more, but we will never see it, not with any telescope, not with any technology, not even with civilizations 1 trillion years more advanced than ours. The prison is absolute. The speed of light combined with the expansion of space draws the line, and nothing on the other side can ever cross it. To picture it, imagine standing in the middle of a foggy field. The mist is so thick, you can only see 100 yards in any direction. You know the field continues beyond the fog, maybe for miles, maybe forever, but you will never glimpse it. The fog defines your world. That's what the cosmic horizon does to us. The universe stretches infinitely beyond what we can detect, but our observable bubble contains only a tiny fraction of it. Astronomers estimate that our cosmic bubble alone contains over 2 trillion galaxies, each one holding hundreds of billions of stars. And yet, compared to what lies beyond, this number might as well be zero. If the universe is infinite, then our 46 billion light-year prison contains exactly 0% of it. Think about what that means. Everything you've ever seen through a telescope, every breathtaking image from Hubble or James Webb, every galaxy catalogued in astronomical surveys, all of it fits inside a bubble that is nothing compared to the greater reality. Entire regions of space are forever beyond our reach. They contain their own galaxies, stars, planets, maybe even other beings staring into their skies and asking the same questions. But no matter how hard either of us tries, we will never know the other exists. The expansion of space has sealed the walls between us. And here's the most haunting part. This prison grows more confining every second. Expansion is accelerating, pushed along by a mysterious force called dark energy. Galaxies that are visible to us now will eventually slip beyond the horizon. Their light will stretch into undetectable wavelengths, and they will fade into the void, leaving behind only silence. Slowly, one by one, the galaxies will vanish until our observable universe shrinks down to just our local group, our Milky Way, and a handful of neighbors adrift in an ocean of blackness. To future astronomers, the grand cosmic story we've uncovered will be erased. They will look up and see nothing but darkness and conclude they live in a tiny, static universe, never suspecting the truth. Our prison isn't just a boundary, it's a ticking clock, erasing the evidence of reality itself. If the observable universe is only a fraction of the whole, the next question becomes impossible to ignore. What lies beyond our cosmic horizon? The temptation is to imagine more of the same: galaxies, stars, nebulae, endless repetition of the structures we already know. And strangely enough, that picture might not just be accurate, it might be unsettlingly precise. Because if the universe is truly infinite, then repetition isn't just possible, it's inevitable. With infinite space and finite building blocks, the arrangement of matter eventually has to repeat, like shuffling a deck of cards forever. At some point, the sequence must recur. That means every possible configuration of atoms exists, not once, but infinitely many times, scattered across distances so vast you could never reach them, yet guaranteed by the mathematics of infinity. It's a disturbing thought. Somewhere out there, another version of Earth orbits another version of the Sun, with oceans, mountains, forests, and cities arranged exactly as ours are. On that Earth, another version of you is reading these words right now. Not metaphorically, literally. The atoms in that person's body are arranged in the same pattern as yours, carrying the same memories, asking the same questions. But in another distant region, the pattern shifts slightly. Maybe you paused before finishing this sentence. Maybe you never picked up the curiosity about the universe in the first place. Maybe your life unfolded in a way that feels familiar but different enough to belong to someone else entirely. Infinity doesn't just allow for this, it demands it. To grasp the scale of this, try to imagine a number so large it makes your mind ache. Physicists have estimated that the distance to your nearest identical copy could be around 10 to the power of 10 to the power of 115 meters away. That number is so absurd that if you tried to write it out in digits, the string of zeros would stretch across more space than exists in the observable universe. Yet if space is infinite, that mind-crushing distance is still finite. Somewhere beyond all horizons, another you exists, living out the same moment, and beyond that, another and another, repeated endlessly. This isn't mystical speculation, it's cold logic. The universe contains a finite number of particle types, arranged into a finite number of possible patterns in a finite volume. with infinite volumes to fill. Those patterns eventually recur. It's the cosmic equivalent of rolling dice forever. Even if the odds are impossibly tiny, infinity guarantees the outcome will repeat, not just once, but an endless number of times. The unsettling consequence is that nothing is truly unique. Your life, your struggles, your triumphs, even your private thoughts, each one plays out in infinite variations across infinite space. Somewhere, another version of you failed at every goal. Somewhere else, another version succeeded beyond your wildest dreams. Somewhere your life unfolded with subtle differences that changed everything. But infinity doesn't stop at repetition. It also demands variation. Not only are there infinite copies of you, there are infinite near misses, worlds almost like ours, but tilted just slightly. Histories where great empires never fell, where catastrophes never happened, or where they happened sooner. Versions of Earth without humanity at all, where evolution followed a different branch. Versions of the solar system where planets formed differently, or where the sun itself never ignited. Every possibility you can imagine exists somewhere in the vastness, and so does every possibility you cannot imagine. This raises a haunting question. What does identity mean if infinite copies of you exist? Are you unique, or just one of countless echoes playing out in the cosmic expanse? Does your story matter if every alternative story is also real somewhere else? Some find this thought exhilarating. Proof that existence is endlessly creative, that nothing is wasted. Others find it terrifying, a suggestion that meaning dissolves into repetition, that we are nothing more than duplicates in an endless machine. But either way, the mathematics doesn't care. Infinity doesn't bend to comfort or fear. It simply unfolds every possibility forever. And yet, even this bizarre vision might not be the whole story, because some scientists believe the repetition we've just described assumes that the universe beyond our horizon looks like the universe we see, smooth, uniform, governed by the same physical laws. But what if it doesn't? What if expansion has carved space into regions with entirely different rules, different particles, different forces, different dimensions altogether? Then beyond the wall of repetition, something even stranger could await. Not just copies of you, but universes where you could never exist at all. If the idea of infinite repetition shakes your sense of reality, then the next possibility tears it apart entirely. Because what if the universe beyond our horizon doesn't just contain more of the same, but instead operates under entirely different rules? This is where the concept of the multiverse emerges, a vast sea of universes, each one born with its own laws of physics, its own constants, its own possibilities. In this picture, our cosmos is not the grand total of existence, but just one bubble floating in an infinite foam of expanding realities. The seeds of this idea sprout from cosmic inflation, that wild moment in the first fraction of a second after the Big Bang when space expanded faster than light could travel. Inflation explains why the universe looks so smooth and uniform in every direction, but it also carries an unsettling implication. What if inflation never truly ended? Quantum mechanics suggests that in some regions, inflation stopped and gave rise to universes like ours. But in other regions, inflation kept going, stretching space endlessly and spawning new universes like a never-ending chain reaction. Each new bubble universe would expand, cool, and develop its own cosmic story, completely cut off from the others. This process, called eternal inflation, implies that the multiverse is constantly growing, constantly birthing new realities, endlessly. Here's where things get mind-bending. Each bubble universe doesn't necessarily play by the same rules as ours. The strength of gravity, the charge of an electron, the speed of light itself, these could all vary from one universe to the next. Most bubbles would be barren wastelands, too unstable for galaxies, stars, or life. Some would collapse almost instantly. Others might stretch endlessly, cold and sterile, but a tiny fraction would be balanced just right, with laws and constants tuned to allow complexity to arise. We happen to live in one of those rare bubbles, not because we're special, but because we could only exist in such a place. This reasoning, known as the anthropic principle, suggests that the universe isn't fine-tuned for us. We're fine-tuned to the universe, but the multiverse concept doesn't stop there. String theory, our most ambitious attempt to unify the laws of physics, requires extra dimensions of space beyond the three we know. In some models, our universe is a three-dimensional membrane, what physicists call a brane, floating in a higher dimensional hyperspace. Everything we see, every particle and force, is confined to this brane, except for gravity, which can leak into the extra dimensions. Other branes might float parallel to ours, separated by less than a millimeter in directions we cannot perceive. Entire universes could be stacked alongside ours, invisible yet unimaginably close. Some theories even suggest that branes occasionally collide, triggering events that look to us like a new Big Bang, filling each universe with fresh matter and energy before they drift apart again. In this view, the universe we inhabit is just one stage in an endless cycle of collisions and expansions, each rewriting the script of cosmic history. And then there are the darker possibilities. If universes can exist with different physical laws, then some might allow for realities we can't even describe. Worlds with more than three spatial dimensions, or where time flows in loops rather than lines, or where forces we don't recognize dominate everything. In such universes, our concepts of matter, energy, and even causality might break down. We can't visit them. We can't interact with them. But the mathematics that describes inflation and string theory hints that they're not just science fiction. They're logical consequences of the equations we already trust. What's unsettling is that the multiverse is, by definition, beyond observation. No telescope can ever peer into another bubble universe. No experiment can confirm the existence of parallel branes. Critics argue that this makes the concept unscientific. If it can't be tested, how can it be considered physics? Yet the equations that describe inflation and string theory demand such outcomes. If we accept the theories, we must accept their consequences, no matter how strange. So, we're left with a paradox. The most ambitious models of the universe imply that ours is only a fragment of a larger reality, but we may never prove it. Somewhere beyond our reach, new universes are being born, each one with its own story, its own physics, its own version of reality. Some might look almost identical to ours, with galaxies, stars, and life remarkably familiar. Others might be so alien that the very concept of existence would feel unrecognizable, and perhaps in a higher dimensional space beyond what we can ever imagine. All of these universes, ours included, are just tiny ripples in an infinite ocean. When you picture empty space, you probably imagine nothingness, a silent void where absolutely nothing exists. But modern physics tells us that this intuition couldn't be more wrong. What we call empty is actually one of the most violent, restless, and creative arenas in the universe. At the smallest scales of reality, space itself seethes with energy, boiling with invisible activity that never stops. Particles appear out of nowhere, vanish just as quickly, and leave behind subtle fingerprints that shape the fate of the entire cosmos. And it is this hidden energy of space, this so-called vacuum energy, that might be driving the most mysterious force in the universe, dark energy. To understand why, imagine zooming into a perfect vacuum with a microscope powerful enough to peer beyond atoms, beyond quarks, all the way down to the Planck scale, where space and time themselves dissolve into frothing chaos, At this level, quantum mechanics reigns supreme, and it refuses to allow true emptiness. Instead, virtual particles flicker in and out of existence, borrowing energy from nothing as long as they pay it back quickly enough. Electron-positron pairs burst into being and then annihilate in less than a trillionth of a second. Heavier, stranger particles do the same in even briefer flashes. Space itself isn't a stage where reality plays out. It's a restless actor, improvising constantly, never still. This endless storm of quantum fluctuations isn't just theoretical, it creates measurable effects. One of the most famous is the Casimir effect. Place two metal plates a tiny distance apart in a vacuum, and virtual particles of certain wavelengths can't fit between them. More particles appear outside than inside, creating a pressure that physically pushes the plates together. You can literally feel the force of empty space. That's how real this so-called nothingness is. But here's the paradox. If you add up the energy of all these quantum fluctuations, you should get a vacuum energy density so enormous it would blow the universe apart in an instant. Theoretical calculations predict a value that's 10–20 times larger than what we actually observe. This is sometimes called the worst prediction in physics, the vacuum catastrophe. And yet, despite this absurd mismatch, the effects of vacuum energy are visible everywhere, written across the stars, because when astronomers look at distant galaxies, they see them racing away faster than gravity can explain. The universe isn't just expanding, it's accelerating. Some invisible pressure is pushing space itself apart. The name we've given this force is dark energy. Dark energy makes up nearly 70% of the total content of the cosmos, outweighing all the matter, radiation, and dark matter combined, and yet we know almost nothing about it. One possibility is that dark energy is simply vacuum energy itself, a constant density of repulsive energy that fills every cubic centimeter of space. As the universe expands, the amount of dark energy increases because more space means more vacuum. The bigger the universe gets, the stronger this repulsive push becomes, and so acceleration feeds on itself, ensuring that expansion never slows down, only grows more violent with time. But this creates a puzzle even more troubling than infinity itself. How can space, which we once thought of as nothing, generate energy from nothing? How can emptiness itself exert pressure, shaping the destiny of everything? Some physicists suggest that vacuum energy balances itself against gravity. While dark energy injects positive energy into the universe, the stretching of space reduces gravitational potential energy, which is negative. The two might cancel out, allowing the cosmos to grow without violating the law of energy conservation. But this feels more like a clever patch than a true understanding. Others suggest that dark energy might not be constant at all. Instead, it could be the manifestation of a new field pervading space, slowly changing with time. If that's true, then the future of the universe depends on how this field evolves. If dark energy weakens, expansion might slow, maybe even reverse. If it strengthens, the cosmos could be torn apart in a catastrophic big rip, where galaxies, stars, planets, and even atoms are ripped into fragments. Right now, the data suggests dark energy is steady, but our measurements aren't precise enough to know for sure. What makes all of this so unsettling is how ordinary space, the very fabric between galaxies, the invisible background of your own room, might be the most powerful entity in existence. It doesn't just hold reality, it drives it. It pushes galaxies apart, dictates the shape of time, and determines how everything will end. The very thing we once dismissed as nothing may turn out to be the ultimate something, the hidden engine of cosmic destiny. When we talk about the expansion of space, it's easy to think of it as just stretching distance. as if galaxies are beads on a string being pulled apart. But expansion doesn't only reshape space, it reshapes time itself. Einstein showed us that space and time are inseparably woven into a single fabric called space-time, so when one stretches, the other must stretch too. This means the flow of time across the universe is not fixed, but is continuously altered by the growth of space, and the consequences of this truth are as bizarre as they are inevitable. Consider what happens when you look at a galaxy billions of light years away. The light arriving in your telescope has been stretched by expansion, turning once blue wavelengths into deep red. But what's less obvious is that the very events unfolding in that galaxy also appear to slow down. A supernova that might brighten and fade in a few weeks nearby will appear to drag on for months or years when it comes from the distant cosmos. Expansion doesn't just stretch light, it stretches time itself. The more rapidly a region of space recedes from us, the more its clock seems to tick in slow motion. At the far edge of the observable universe, time appears to crawl compared to the present moment in our local region. This creates a strange and humbling paradox. From our vantage point, the universe is 30.88 billion years old. But if you could somehow observe from a distant, rapidly receding galaxy, our local space might appear to be much younger, its history unfolding more slowly. There is no single universal now. Each location in the universe carries its own definition of the present. This shatters the simple idea that the universe has one shared clock. Time is local, not global, and cosmic expansion only makes the differences more extreme. But the implications go further. In the dense early universe, when space was compressed to a fraction of its current size, time itself flowed differently. Processes that now take billions of years, like the birth of galaxies or the clustering of stars, happened much more quickly because time was packed as tightly as space. In a sense, the universe has been aging unevenly, with the early cosmos racing forward and the present cosmos stretching time like a rubber band. This means cosmic history isn't just a record of expanding distances, it's a record of the changing tempo of time itself. So where does this leave us when thinking about the future? As dark energy accelerates expansion, the stretching of time becomes even more extreme. Distant galaxies already appear to slow down from our perspective, but in the far future, their clocks will seem to freeze entirely. Civilizations looking into the night sky billions of years from now will see the cosmos come to a halt beyond their local group of galaxies. The stars and galaxies we marvel at today will fade not because they've disappeared, but because expansion has stretched both their light and their time into invisibility. Eventually, the accelerating expansion will lead to a lonely cosmos, where only our merged local galaxies remain, and even those will dim as stars exhaust their fuel. Time, from the perspective of future observers, will appear to stretch so thin that events unfold in near silence. The universe won't just become darker and emptier, it will become slower, as though reality itself is running down. And if dark energy continues its relentless push, there may come a point when even the binding forces of atoms can't keep pace. In that scenario, time itself could tear apart along with space, breaking down the very order that makes causality possible. But even if the universe avoids that catastrophic fate, the final destination still appears bleak. Heat death. The slow fading of everything into uniformity represents not just the spreading of matter into thinness, but the slowing of cosmic time into near stillness. Stars will vanish, black holes will evaporate, particles will scatter, and the arrow of time itself may lose its meaning in a universe without differences, without processes, without change. This is perhaps the most profound consequence of expansion. It doesn't just determine where the universe is going, but how time itself will be experienced along the way. From the frantic ticking of the early cosmos to the stretched silence of the far future, the expansion of space is also the expansion of time. The very stage on which existence unfolds is being rewritten with every passing moment, carrying us toward a future where not just matter and energy, but time itself may vanish into emptiness.